Hello again. So in this problem 6.58, we have a DC circuit, DC bias circuit with a PNP BJT. Okay, so it's a PNP BJT. Again, because of the arrow, so the arrow is pointing inside the BJT. So we have the emitter up here, right? This is the resistance, so the emitter here. We have the collector here, and we have the base here. And we don't know anything about the circuit except the common emitter current gain beta up here, so it's 40 in this case. And for the first analysis, we know that RB is equals to 20K. Okay, so those are the information that we have. We also have this voltage source up here at the emitter plus 3 volts, and this minus 3 down here connected to the collector resistance. So this problem, it has three parts. The first part is that we are going to consider that beta equals to 40 and the base resistor as 20K, and we need to define VB, VC, and VE. Then we are going to change that base resistance to 100K, so we will increase RB to 100K, and we are going to define again VB, VC, and VE. Now, because probably we are going to get VB, VC, and VE different in this configuration here, it's different than in this one here. The third part, we are basically going to define a new common emitter gain. Remember, this is a parameter from the BJT, that the voltage that we get with the base resistance of 100K ohm is the same as the voltage that we got when we analyze the circuit in part A with the resistance, the base resistance 20K ohm. Okay, so let's start with part A. Okay, so for part A, one thing is that we should first assume that the BJT is operating in the active mode region. Okay, so for this NPN transistor, it means that VEB is equals to 0.7 volts. So this potential here, let me draw it here, from this terminal to that terminal is 0.7 volts. Okay, now if we look at this circuit from the base and emitter terminals, we can apply a loop analysis here. Okay, and with that loop analysis, we can define either the base current or the emitter current, considering that for the active mode operation, we know that the current at the base, right, current at the base is equals to the current at the emitter divided by beta plus 1. So we know this relationship here from our assumption that the BJT sorry, is operating the active mode region. Okay, now if we write the equation for this loop here, okay, call loop 1, okay, and we start up here at the plus 3 voltage source, from because we have, so we can represent this plus 3 here as a plus minus ground here that connects to this terminal, and because we adopt this the direction of the current going clockwise, we are first entering the negative terminal of this voltage source, which is indeed 3 volts, right? Let me just we write here, it's 3 volts. So the first term in our loop analysis is that minus 3 volts from the voltage source. After we cross this voltage source, we pass through this emitter resistance, and the voltage drop across this resistor is plus Re times the emitter current. Once we pass this Re, we need to cross this voltage source, right, from the PN junction of the BJT, which is plus 0.7 volts because we are entering the positive terminal. So it's plus 0.7 volts. And now we just need to cross the base here, right? So we're just crossing the base here, which is a voltage drop of Rb times Ib. And that should be equals to 0, right? From Kirchhoff's law. Now, because we are assuming active mode operation, we have this relationship here that we can plug in IB here, and then we'll have a single equation that basically gives us the value of the emitter current. So if we rearrange the terms in this equation, okay, basically we have IE that multiplies the first term is the emitter resistance, is this term here. Now if we substitute IB equals to IE divided by beta plus 1, the second term inside this parenthesis is going to be plus RB. Now IB becomes IE divided by beta plus 1, so this RB divided by beta plus 1, right? That's the terms that involve the emitter current. So we are done with this term here. Now this minus 3 adds with this plus 0.7 and it becomes minus 2.3 volts. And if we pass them to the right hand side, it becomes 2.3 volts. Okay, here we have resistance times current is a voltage that's equals to some voltage. Now if we isolate IE here, we get 2.3 volts divided by RE plus RB divided by beta plus 1. Now we know the emitter resistance, right? It's a known value from the circuit. We know the base resistance for this first part. Let me just draw up here again. So RB is equals to 20k. And we know beta, which is 40. Okay, so if we plug in those values in this equation here for IE, we get IE equals to 0.855 milliamps. So that's this current here that's flowing through this emitter resistance, right? That's coming inside the BJT. Now, because we again assumed active mode operation, we know that the current at the collector, IC, is equals to alpha times IE. And this means IC equals to 40 divided by 41 times 0.855 milliamps. And this current IC becomes 0.834 milliamps. Okay, so this is the current IC. Now for IB, we could take the difference, right? We know that IB is equals to IE minus IC, which is the same as IC divided by beta. And in this case, IB, the current that's flowing through this resistor here. So we already calculated this current here, right? This is IC, this is IB. If we plug in the values of IC here, so this one here, and beta equals to 40, right? We get a current at the base that is 0.021 milliamps or 21 microamps. So now we have the currents, all the currents that we need, right? We have the emitter current, we have the base current, we have the collector current. So we can start calculating the voltages that we need to define for this problem. So the first voltage, VE, is going to be equals, so because we know we can calculate the voltage drop across this 2.2 here, so I'll call VRE, right? We know that V, so let me just erase here, VRE is equals to 3 volts minus VE, that equals to IE times 2.2 k ohm, right? Just using Ohm's law. Now, if we isolate VE in this equation, we get 3 minus 0.834 times 2.2. And here I'm just ignoring this k because we have milli here. So 10 to the 3 times 10 to the minus 3 gives us 1, right? So it's just minus 0.834 times 2.2. And this voltage, VE, is equals to 1.12 volts. So we know VE. Now, if we want to calculate the other voltages, we can apply a similar analysis. So for VB, we know that here this terminal of the base resistance is grounded, right? So this is VRB. And we know that the voltage at this terminal here is actually VB. So VB in this case is just RB, the base resistance, times the base current, which is equals to 20k times the current at the base, that is 21 microamps. So the voltage at the base, VB, is equals to 0.42 volts. Last but not least, we can calculate the voltage here across this 2.2 k ohm at the collector, so we'll call VRC. And we know that the voltage, because we are assigning positive here, negative here, which agrees with the direction of this current, right? So we must be concise with the assumptions of the currents and the voltages, right? So this polarity here agrees with the direction of this current. We can take VRC equals to VC minus those minus 3 volts that we have here, right? And that's equals to IC times the collector resistance. So if we isolate VC, we get IC RC minus 3 volts. And if we substitute the values of IC and RC here, we get VC equals to minus 1.1652 volts. Now remember that our assumption is that the BJT, okay, so the BJT here is operating in the active mode. So from that we know this voltage here, that's the first, so we assume that it's operating in the active mode region, so we know that this potential difference here is 0.7 volts. This allows us to start analyzing this circuit. But now that we calculated the values of the voltage VE, VB, and VC, we still need to verify that the second condition for the BJT operates in the active mode region, it still holds. So in this case, because it's a PNP transistor, we must have VCB, which is less than 0.4 volts, right? Which means that VC should be less than 0.4 plus VB. And in our case, we have something that's negative here for VC, so it's minus 1.1652. Should be less than VB plus 0.4, and VB is 0.42, right? So minus 1.1652 is less than 0.82 volts. So our first assumption that the BJT is operating in the active mode, it holds. And the values of VB, VE, VC that we calculated here basically holds, they're correct, okay? And remember that this assumption allows us to use these equations here, right? So this equation here, and let me see another one I think we didn't use, so this, also this one here, they all come from the condition that the BJT is operating in the active mode region, okay? So that's why we assume active mode operation. We know this one here, and then we are allowed to use these relationships using the common emitter current gain and the common base current gain, beta and alpha, to establish these relationships between currents, okay? So, and that's it, okay? So that's the first analysis. So we are done with part A. Now for part B, we are just changing the value of RB, okay? The value of RB to 100K. But beta is still 40. So we are just changing the value of RB, okay? And the analysis of this problem, it's just the same as we did in part A. Okay, we have just changed the value of RB here to 100K. So again, we assume active mode operation. We still have this 0.7 here. We again can apply a loop analysis in this closed loop here, which gives us minus 3 plus RE times IE here. Then we cross this 0.7, so it's plus 0.7, and then we cross here plus RB times IB equals to 0. And remember that IB, if we are assuming active mode operation, is equals to IE divided by beta plus 1. Okay, so if you rearrange this equation again, if we substitute IB here using IE, we get IE equals to that minus 3 plus 0.7 goes to the right hand side, becomes 2.3 again, divided by the emitter resistance, so it's 2.2K, this one we didn't change, plus the base resistance, which now is 100K, divided by beta plus 1, which is 41. So in this case, this emitter current, okay, it's now 0.4958 milliamps. And just for you to remember, in the previous analysis, this value was 0.855 milliamps. So by increasing, if we keep the common emitter current gain beta the same, 40, and we increase the base resistance, right, to 100K, in this case we are decreasing the value of the current at the emitter, okay? We are decreasing the value of IE. Now we can proceed calculating IC, so I will keep using blue here for the current so we can contrast with the previous values, okay? So we know that the collector current is equals to alpha times the current at the emitter. And we know alpha, it's 40, remember beta divided by beta plus 1, times that 0.4958 milliamps. And this gives us an IC that's equals to 0.4834 milliamps. And for us to remember the previous value of IC, it was 0.834 milliamps. So we also decreased the collector current, right? And the last current, so we calculated the collector current here. We calculated the emitter current up there, right? This one here. Now we need to define this base current here. And this base current we can calculate using either the difference between IE and IC, right? So it's IE minus IC, or it's just IC divided by the common emitter current gain beta. So IB is equals to that 0.4834 milliamps divided by 40. Okay, so IB in this case is equals to 12.085 microamps. And now the base current has also decreased, because in the previous analysis we had 21 microamps. And that makes sense, right? Because we are increasing this resistance here, right? This resistance at the base, this one here. So we are making more difficult to current to flow through this resistor, right? And if you are keeping the common emitter current gain constant, the same 40, and we know that the relationship of IB and IE is actually beta plus 1 times IB. If we reduce the base current right here, we are reducing the current that's flowing through the collector. And that's when the third part C, comes into play. Because on part C, we are going to modify beta in order to keep the same emitter current and keep all the voltages across, VE, VC, and VB the same. So still in part B, we didn't define the voltages, right? So we just applied the same methodology. So because we now know all the current, so we know IE here, we know IB, and we know IC here. We can calculate those voltage drops. So VRE can calculate VRB, and we can calculate VRC. And with those voltages, we find VB, VE, and VC by just applying Ohm's law, right? So it's very simple. We take, for VE, we take those, so VRE is equals to those 3 volts that we have up here, minus VE equals to IE that multiplies RE. This gives us a VE that's equals to, let me see here, 1.9085 volts. For the base, okay, we have VRB that's equals to the potential difference, so VB minus 0, right, because it's grounded. That should be equals to IB times RB. And this is the 100K that we are using now. So in this case, VB is equals to 1.2. Sorry, 1.2085 volts. And for, let me just duplicate this one here. So for VC, we know that VRC right here is equals to VC minus those minus 3 volts, right? That's equals to RC times IC. We know RC, we know IC, so VC becomes RC times IC minus 3 volts, and this gives us a VC equals to minus 1.9365 volts. Okay, and if we want to compare with the previous values, so VE, it was 1.12, VB, it was 0.42 volts, and VC, it was minus 1.1652. Now, remember that we assumed active mode operation. And for active mode operation of a PNP transistor, we must have VCB that is less than 0.4 volts. So our VC must be less than 0.4 plus VB. And this gives us a VC, right? So we know VC, it's minus 1.9355 less than 0.4 here times the base current here, which gives us 1.6005 volts. So this again holds, and our assumption for active mode operation, it's still valid. Okay, so it's okay. And then we are done with part B. Now part C, remember, we have changed the value of RB. So let me just copy this one here again. To a new page. So we have changed RB to 100K. But now, since we change RB, the values of the voltage VB, VE, and VC, they've also changed, right? Because we kept beta the same. So beta, it was 40. Now, if we want to keep VB, VE, and VC the same, we need to pick a different transistor, different BJT, that has a different beta. And what's the value of this new beta in order to keep the same voltage? So we know that the voltage VE, right, this voltage VE here, we can calculate by figuring out the voltage drop across this VRE. And this voltage drop VRE is actually the current IE times the resistance IE, right? This is VRE, which is the same as 3 minus VE. So one thing is that we must keep this, if we are not changing the emitter resistance, we must keep this current IE the same in order for VE in this equation stays the same. And this VE here should be the same value of VE from part A. So in our case, VE for part A, it was 1.12 volts. That's what we have. So we need to select the beta based on this condition, okay? So if we look at this loop here again, we still have that equation that IE is equals to that 2.3 volts divided by the emitter resistance plus the base resistance divided by beta plus 1. So if we need to keep this IE the same as the first analysis, which was 0.4958, right? 0.4958. We must select a new value of beta that gives us that same, so this right hand side here should be equals to that 0.4958, okay? And we can isolate beta plus 1 in this equation, right? So we can manipulate, so we can put this denominator here multiplying IE up here, and then we can put, so let me do it here. So IE times RE plus RB divided by beta plus 1, right, should be equals to that 2.3 volts. That 2.3 comes from this, because we are assuming active mode operation, so we know this 0.7 here and that 3, so 3 minus that 0.7 gives us those 2.3. Now, this quantity here, we know IE times RE. We also know IE times RB, and we want to define a new beta plus 1. So we can rearrange again this equation by taking RB times IE, right, divided by beta plus 1. That's equals to 2.3 volts. And because we want to isolate beta plus 1, we take this IERE goes to the left hand side minus, so it's minus IE times RE, right? And now we can actually isolate beta plus 1. So if we put this one here, multiplying this entire thing here, right? And then we take this 2.3 minus IE divided by IE, we get beta plus 1 equals to IE divided by 2.3 minus IE. Okay. In other words, beta should be equals to IE divided by 2.3 minus IE minus 1. So we know RB is now 100K. We know IE, so IE should be the value of IE when we had the 40, the common emitter current gain of 40 and RB equals 20, so this current is 0.85 divided by 2.3 minus those 0.85 milliamps times those 2.2 K ohm minus 1. So this gives us beta equals to 100, sorry, not 100, 204 minus 1, which gives us a beta of 203. So if we, and because we have this, now this current IE here, which is the same, right? Basically the currents at the collector and the base will provide the same voltage drop across these resistors, right, RC and RB. That would give us the same VB and VC. So just to summarize here, in this part C, we basically need to change this BJT here to a BJT with a higher current emitter, with a higher common emitter current gain, beta, that with a new RB of 100K gives us the same voltage as VB, VE, and VC. So I'll leave it to you to recalculate, so reanalyze the circuit, which is the same method that we apply in part A and B, and figure out the values of VB and VC and VE if they actually match with the first case in part